Another simple stresses are shear and bearing stresses. And for shear stress, forces parallel to the area resisting the force cause shearing stress. It differs to tensile and compressive stresses, which are caused by forces perpendicular to the area on which they act. Shearing stress is also known as tangential stress, and the formula for shear stress, tau, is equal to V all over A. V is the resultant shearing force which passes through the centroid of the area A being sheared. So we have a single shear and a double shear. And we have an overlapping of plates with a bolt and a force P. And for double shear, we have two plates overlapping a single plate. And if we have a direction of P for a double shear, which is 1/2 of P and another 1/2 of P. And bearing stress. It is the contact pressure between the separate bodies. It differs from compressive stress as it is an internal stress caused by compressive forces. And the formula for bearing stress, sigma sub B is equal to P sub B all over area sub B. And for the diagram for the bearing stress, we have the force P, B, and we have an overlapping of plates with a bolt, and the area for bearing area, which is the diameter of the bolt multiplied by the thickness of the plate. Example number 1. What force is required to punch a 20 mm diameter hole in a plate that is 25 mm thick? The shear strength is 350 meganewton per meter square. So we have here a diagram. We have a plate which is 25 mm thick and a puncher with a hole of 20 mm diameter and a force P. And the punch out, we have a shaded area which is the circumference of the circle and multiplied by the thickness of the plate. Let's solve for the value P required given. And the given are, we have 20 mm diameter hole, or D is equals 20 millimeter, and the thickness of the plate T is equals to 25 millimeter, and a shear strength, or the tau, it is equal to 350 meganewton per meter square. And we're going to find the value P by using the formula for the shearing stress or shear stress. We have tau is equals to V over A. And what is A, or the area? The area is the punching out area, which is the circumference of the circle multiplied by the thickness of the plate, or pi d times t, and pi multiplied by the diameter of the punching hole, which is 20 millimeter, and the thickness of the plate, which is 25 millimeter, and equate to 1570.8, and it is in millimeter square, and this is for the area. And we substitute the tau value. So this is the 1, we have the tau value, which is 350, and equate to V or P, and we divide by 1570.8, and the value for P is equivalent to 549,778.7 Newton, or in terms of kilonewton, it is 549.8 kilonewton, and that's the required force P. Example number 2. A hole is to be punched out of a plate having a shearing strength of 40 psi. The compressive stress in the punch is limited to 50 psi. A. Compute the maximum thickness of plate in which a hole 2.5 inches in diameter can be punched. And B. If the plate is 0.25 inch thick, determine the diameter of the smallest hole that can be punched. So here's the diagram. So a force P and a hole which is 2.5 inch diameter with a limited compressive stress of 50 psi and a shearing strength of 40 psi. So given we have the stress or punching stress, which is equivalent to 50 psi, then the shear stress tau is equal to 40 psi, the diameter, which is 2.5 inch. And for A, we need to compute the maximum thickness of the plate. So T is in question. By using the puncher's strength, P is equal to sigma times A, and A is equal to the area of the hole, which is pi over 4d squared. Then substitute at 1. So P is equal to the compressive stress, which is 50 psi, and multiplied by the area, which is pi over 4, and the diameter is 2.5 inch squared. So P is equal to 50 times pi times 2.5 squared all over 4, and the value is 245.44, and it is in kips or kilopounds, and that's for puncher strength. And once we got the value for P, next for the shear strength, the formula V is equals to tau multiplied by A, which is equivalent to equation number 2, where A, for the shear strength, it is equivalent to the circumference multiplied by the thickness, or pi d times t, and V equate to the punching force, which is equivalent to P, and substitute at equation 2. So at 2, V, which is equal to P, or 245.44 kips, is equal to tau value, which is 40 psi, and and multiplied by the area, which is pi, and the diameter is equal to 2.5 inch, and the unknown value, which is equal to t. And we have t, or 245.44 divided by 40 pi times 2.5, and t is equal to 0.781 inch, and that's the thickness of the plate. And that's for letter A. So this is for letter A. What about letter B? If the plate is 0.25 inch thick, determine the smallest diameter of the hole. So by using the compression of puncture, for the compression of puncture, we have P is equals to sigma times A, and the sigma is 50 psi, then multiplied by the area, which is pi over 4d squared, pi over 4, and the diameter d squared, and this is for P. Next, for the sharing of plate, which is V is equal to tau of A, where V is equal to the force P, which is equation 3. V is equal to tau of A, then substitute V for P, which is 12.5 pi d squared is equal to the tau value, which is 40, and multiplied by the area, which is the circumference times t, so pi d, and multiplied by the thickness, which is 0.25 inch, and cancel out d and cancel out pi, and the value for d is equals to 40 times 0.25 divided by 12.5, and d is equal to 0.8 inch. Another example. Find the smallest diameter bolt that can be used in the clevis if P is equals to 400 kilonewton. The shearing strength of the bolt is 300 megapascal. So we have this diagram, and we have to find the value of the smallest diameter of the bolt to be used. Given P, the force P, which is equivalent to 400 kilonewton, the shear strength is 300 megapascal, or meganewton per meter square, and we need to find the value or the diameter of the bolt. So we have here a double shear, which means double shear, and for shear, the formula V is equals to tau of A, and that's equation 1. And for the area is equivalent to, because it is a double shear, it is twice of pi over 4 d squared. And at 1, V is equivalent to P. V is equal to P, which is 400 kilonewton, and multiplied by 1000 and equate to the sigma, which is 300 megapascal, and multiplied by the area, 2 times pi over 4 d square, and d squared is equal to 400,000 times 4 and divided by 300 times 2 times pi, and d is equal to, so 400,000 times 4 divided by 300 times 2 times pi, and the value of that is square root of 848.82, or d is equal to 29.13 millimeter. So that's the smallest diameter of bolt to be used. Another example. In figure 1-12, assume that a 20 millimeter diameter rivet joins the plates that are each 110 millimeter wide. The allowable stresses are 120 megapascal for bearing in the plate material and 60 megapascal for shearing of rivet. Determine A. The minimum thickness of each plate, and B. The largest average tensile stress in the plates. So we have here the plate with a 110 millimeter wide and a force P with a rivet of 20 millimeter diameter given. We have the diameter of the rivet, which is 20 millimeter, the width of the plate, which is 110 millimeter, the bearing stress is 120 megapascal, and the shearing stress of the rivet is equal to 60 megapascal. And for A, at A, we need to find the minimum thickness of the plate. We need to find the force P based on shearing of rivet. And the formula, P is equal to tau times A, and the value for the shearing stress, it is 60 megapascal, and we multiplied by the cross-sectional area of the rivet, which is pi over 4 d squared, or 20 squared, and P is equal to 18,849.6 Newton, or it is equivalent to 18.85 kilonewton. Once we have the value for P, we need to use the bearing of plate to find the value of T. From bearing of plate, we have P for bearing is equal to the bearing stress and multiplied with the area of the bearing. And for the area of the bearing, it is equal to the diameter of the bolt multiplied by the thickness. And we use P, which is 18,849.6, is equal to the bearing stress, which is 120 megapascal, and multiplied by the area of the bearing, which is the diameter is 20 mm, and the thickness. And the value for the thickness of the plate, 18,849.6, we divide by 120 times 20, and the thickness is equal to 7.85 millimeter, and that's the thickness of the plate. For B, the largest average tensile stress in the plates. So we need to find the value of the tensile stress. So tensile stress, which is equivalent to P equal to sigma times A, where A is equal to the thickness of the plate and multiplied by the net area of the plate, which is the width less the diameter of the bolt, or W less diameter, at 1, where P is equal to 18,849.6 is equal to the tensile stress and multiplied by the area T, and the thickness is 7.85, multiplied by the width of the plate, which is equivalent to 110, and subtract to the bolt diameter, which is 20 millimeter. Sigma is equal to 18,849.6. We divide by 7.85, and 110 minus 20, it is equivalent to 90. And the tensile stress is equal to 26.67, and the unit is in megapascal. Example: the lap joint is fastened by 4 3/4 inch diameter rivets. Calculate the maximum safe load P that can be applied if the shearing stress in the rivets is limited to 14 psi and the bearing stress in the plates is limited to 18 psi. Assume the applied load is uniformly distributed among the 4 rivets. So we have here the overlapping of plates, and we have 4 rivets, and the thickness of the plate is 7/8 inch, and the diameter of the rivets is 3/4 inch, with the width of the plate, which is 4 inches. We have the diameter of the bolt, which is 3/4 inch. The shearing stress is equal to 14 psi. The bearing stress, which is equivalent to 18 psi. So let's solve first the value of P using the shearing of rivets. Shearing of rivets. Okay, so P is equal to tau of A, where A is the area of the circle. So equate to the shearing stress is 14 psi multiplied by the area, which is the area of the circle, pi over 4, and 3/4 inch squared. So the value for P is equal to 24.74 kips or kilopounds. Next, bearing of plate. Once we got the value of P, we can use that value to find P is equal to the bearing stress multiplied by the area of the bearing. And we have for P is equal to bearing stress, which is 18 psi, and for the area of the bearing is equal to 4 times the rivets multiplied by the diameter of the rivet and thickness of the plate. So we have 4 times the bolt or rivets, and then the diameter of the rivets, which is 3/4 of inch, and multiplied by the thickness of the plate, which is 7/8 inch. And P, 18 times 4 times 3/4 times 7/8, and the value for P is 47.25 kips. The maximum safe load should be used, or P maximum is the value which has the lowest value for 2P, and the maximum value for P is equal to 24.74 kips, which is the safe load. And our last example, in the clevis, find the minimum bolt diameter and the minimum thickness of each yoke that will support a load P, which is equal to 14 kips without exceeding a shearing stress of 12 psi and a bearing stress of 20 psi. So we have here the diagram. We have a double shear, the bolt, and we need to find the diameter of the bolt and the thickness of the yoke. First, given. And the given, we have P 14 kips and the shearing stress, which is equivalent to 12 psi, and the bearing stress, which is equal to 20 psi, using the shearing of rivets. Shearing of rivets. And this is a double shear. So the formula is P is equal to the shearing stress multiplied by the area, and P, which is 14 kips, is equal to the shearing stress, which is 12 psi, and multiplied by the area. So what is the area for the shearing of rivets? Because it is a double shear, so therefore we have the area is equal to twice the area of the bolt or the circle. So twice of the area of circle or the bolt, which is pi over 4, and multiplied by d squared. D squared is equal to 14 times 4, and we divide by 12 times 2 times pi, and d is equal to 0.8616 inch, and this is the diameter of the bolt. Diameter of bolt. Next, to find the minimum thickness of the yoke, we use the bearing stress. So bearing of yoke And the formula, P is equals to the bearing stress multiplied by the area of the bearing, where area of the bearing is equal to twice of the diameter multiplied by the thickness, and P is equal to 14 kips and equal to the bearing stress, which is 20 ksi, and multiplied by the area of the bearing is twice of the diameter, which is equal to 0.8616, and multiplied by the thickness of the yoke, and T is equal to 14 kips divided by 20 times 2 times 0.8616, and T is equal to 0.4061 inch, and this is the thickness of yoke.